Hello friends, welcome back to lecture 4. I am Dr. Milind Meshram, working as an assistant professor in the Department of Chemistry, KTHM College, Nashik. So today I am going to talk about multiple step synthesis. So in this I will be discussing on guideline number 3. Before going to start this guideline number 3, I would like to talk about the previously described guideline 1 and guideline 2. Guideline 1 says that your disconnections must correspond to the non-reliable reaction, and guideline number 2, when you consider any target molecules which is consist of two parts and joined by the heteroatom, so your disconnection should be next to the heteroatom. So in this lecture I am going to talk about the guideline number 3, and these guidelines are being used in the retrosynthetic analysis. So this guideline number 3 says, so we should consider the alternative disconnections and we should choose the appropriate route that avoid the chemoselectivity problem. So let's see how these guidelines are useful in the retrosynthetic analysis. So for this purpose we chose target molecules. This is actually intermediate of potential anti-obesity drug, that is ICI D7114. So when you look at this molecule, you will spot the various functional groups over here. So when you look at this molecule, so you will spot these three functional groups, these ether linkages, two ether linkages, amino functionalities. So first of all we need to find out how many possible disconnections are there in it. So let's have the possible disconnections. I have already drawn over here A, B, C and D. First of all we will see the disconnection A. Disconnection A will give the fragments. So these are the idealized fragments, so we call them as a synthon. So this NH tend to have the negative charge, since it is more electronegative than the carbon, so it tend to have negative charge. And this if you transform this synthon into its chemical equivalent reagent, so it will be NH2, so amine. Basically it is amine. So next synthon is, this carbon is having positive charge, so we would have the benzyl bromide. Now next disconnection is B. So when you cleave this CN bond, you can write over here CN amine bond like this. So you will get these two fragments. One is having NH negative, so it is you can have the benzyl amine as a chemical equivalent, and this carbon is having positive charge, so we can attach bromide, chloride and any living group. So you will have the real chemical reagents, so that are useful in the forward synthesis. So let's have a C cleavage. So in this you have CO linkage. Okay, so when you cleave this CO bond, so you will have these synthons. One carbon is having positive charge, so you can add bromide over here, so you will get the alkyl bromide, and here the phenoxide ion. So proton get attached over here and it will become the phenol. So these are the real chemical reagent. So let's move to the decleavage. So after cleaving this bond, so you will have these synthons. So this is basically to benzyl bromide and this is phenol. So when you we have in this way we have the 4 possible disconnections. So out of which when you consider this C and D, both the C and D disconnections pose a chemoselectivity problem. Okay. When you are going to alkylate at the phenol, so in the presence of amino functionality creates a chemoselectivity problem. Similarly, here also when you are going to alkylate this phenol, say in this phenol structure, so you will have the amino functionality, so that will create a problem in chemoselectivity. So then we have the disconnection A and B. Okay, so we have a disconnection A and B. So if you consider B route, so that would be the better option, because after disconnecting A, so you will have to be alkylate add oxygens in the presence of this amino functionality. Okay, so to avoid this chemoselectivity problem, we need to install this more reactive functionality in the end. So let's consider the B cleavage. So that is CN cleavage. So you will get this NH negative. So it can be transformed into benzylamine, and this positive charge will acquire bromide. So you will get the bromo derivative. So let's consider this as our target molecule. Then when you look at these molecules, so you will spot the 2 ether linkages. So one is E and F. So as I told you before, so as the guideline tells us, we need to choose alternative route to avoid the chemoselectivity problem. That means we need to disconnect more reactive functional group. So this bromo-ethyl group is more reactive than the benzyl group. So let's consider, let's see the cleavage E first. When you cleave this CO bond, so you will get these 2 fragments. So I already written as a directly chemical equivalent, that is phenol, and one more is a phenyl cation, benzyl cation. So it will have the benzyl bromide. So in this case, when this connection requires alkylation, but this itself is acting as a alkylating agent, so it will cause a chemoselectivity problem. To avoid this problem, so we'll go for this disconnection F. So it will give a protected phenol, and when you have when you cleave this CO bond, so you will get this phenol and this dibromoethane. So further when you cleave this CO bond, so you will get readily accessible hydroquinone and this benzyl bromide. Okay, this is all about retrosynthetic analysis. So let's move to the forward synthesis. Forward synthesis of intermediate ICA D7114. So when the treatment of hydroquinone with benzyl bromide in the presence of base, so you will get the protected product. So here selective benzylation can be easily achieved. Okay, so in next step, when you treat this phenol means phenolic OH, when you treat with this phenol with dibromoethane in the presence of base, so you will get this bromo derivative. and eventually when you treat with the benzyl amine, so you will get your target molecules. Okay, this is all about the retrosynthetic analysis and its synthesis. Okay, let's move to a very important topic that is being used in the retrosynthetic analysis, functional group interconversion. It is generally abbreviated as FGI. So what is the functional group interconversion? Just transformation of one functional group to another functional group to facilitate the suitable disconnection. Okay, so let's have an example. This is an antihypertensive drug aponine. When you look at this molecule, you will spot the two functional groups. One is amide and second one is amine. So we should know how these functional groups can be made. So we will apply the guideline 1. So for example, guideline 1 says that our disconnection must correspond to the non-reliable reaction. Then second guideline suggests whether our target molecule is having heteroatom or not. If it is having, then try to disconnect the bond next to the heteroatom. And third guideline suggests that so we have to choose alternative disconnection to avoid the chemoselectivity problem. So let's have a retrosynthetic analysis for this particular molecule. So we need to find out the possible disconnections. First of all, we will go by the guideline 2. So since our molecule having the heteroatom, so we will cleave the bond next to the heteroatom. So let's have a cleavage, D cleavage. When you cleave this bond, CN amine bond, so you will get these fragments. So these fragments can be converted into its chemical equivalent reagents. So when you look at this newly generated molecule, here you will observe that this amide is difficult to prepare in the presence of this resulting amino group. Okay, that means it poses a chemoselectivity problem. So then we will go for another cleavage, that is A cleavage. So when you cleave this CN amide bond, so you will get these reagents. I have already written reagents rather than their synthons. So let's consider this molecule. Even these disconnections have greater difficulty in making this amino functionality in the presence of this acid chloride. That means it will create the problem. So what is the solution? So we know this acid chloride can be obtained from its corresponding acid by using a interconversion. Okay, so let's have a functional group interconversion. So transformation of this acid chloride into its acid, not a disconnection, just interconversion from one functional group to another functional group to facilitate suitable further disconnections. So since this molecule is not commercially available, so we will go for further disconnections. As our guideline says, if our molecule contains heteroatom, so our disconnection should next to the heteroatom. So let's disconnect this bond to get the simpler starting material. Okay, so when we disconnected this bond, that is CN amine bond, so we got this anthracyclic acid and chloropyridine. So this is all about the analysis. So what we have done in this analysis is that first of all, in first step we have we have seen this molecule and check the possible disconnections in it. Okay, so we have checked whether these functional groups made by the non-reliable reaction or not, whether our target molecule contains heteroatom or not. If it is contained, then we try to disconnect this bond next to the heteroatom. Then third step, we have checked the alternative disconnection to avoid the chemoselectivity problem. And finally, we have used the functional group interconversion to facilitate the further suitable disconnections. Okay, so next, let's move to forward synthesis molecule for 9. Okay, its synthesis is very simple. So in the end, we have got the anthranilic acid. So the treatment of this anthranilic acid with chloropyridine would give this protected amino product. Then we can treat it with thionyl chloride to give the acid chloride. It is the standard way of making the acid chloride from its corresponding acid. And finally, the treatment of this acid chloride with secondary amine would give this our target molecule. This is all about the synthesis. So friends, I hope you enjoyed this lecture and understood as well. In next lecture, I will take more interesting problem based on these guidelines and functional group interconversion. Thank you very much.